Welcome everyone to today's GOCC talk. We'll be hearing from Veronica on dihedral sign patterns in M0N. Before we get started, let me quickly remind you of our community statement. We are all learning, everyone has something to contribute, and no one has all the answers. So with that, Veronica, go ahead and get started whenever you're ready.
Yes, thank you, Bailey, and thank you for inviting me. So yes, today I want to talk to you about a project that I did with Hannah Tillman-Morris. And if time permits, I'll talk about some work in progress that is related. Please feel free to stop me if you have any questions at any time. And so the story I want to tell you today is about a very special parametrization of M0N and sign patterns in this parametrization. So the idea is that I'll start talking about what this parametrization is sometimes found in the literature as the dihedral coordinates on M0N. And then I want to get more into what sort of our work was more focused on, and is looking at sign patterns in this particular set of coordinates. So I will do this in two steps. First, I will talk about something that we call realizable sign patterns and related to the connected components of the real points of M0N. And then I will talk about consistent sign patterns, which is a slight generalization. And the work in progress, if permitting, just to throw some keywords in case anyone would be interested to talk at some point, is about positive geometries from toric blowdowns of M0N. So we'll see if we get there. Okay. So first, let me just quickly say what is M0N in case some of you have never encountered it. So this is the moduli space of n-mark points in the projective line. And I'm going to give you a very explicit parametrization of how we can view this space. So if we have a point in M0N, we are going to represent it by a 2 by n matrix, where we're going to view the columns as the marked points in P1. So this 1zi will be projective coordinates. And note that really everything is happening under PGL2 symmetry. So this means that a point is not really represented by a unique matrix, but by some PGL2 orbit of matrices. And also because of this same reason of our PGL2 symmetry, we can, without loss of generality, do what sometimes is called the gauge fix, which means that we can set one point to be 0, one point to be 1, and one point to be infinity. Okay, so we are going to want to work with some projective invariants of this moduli space. And some very nice projective invariants are what are called Cross ratios. So let me give you the very explicit definition. If we have 4 points in P1, then we define their cross ratio as a very nice Laurent monomial. So we are just going to take Z1 minus ZK, Zj minus ZL, Zi minus ZL, and Cj minus Zk. And we take this nice product. This can also be represented as this Laurent monomial on the Plucker coordinates, and this is why we can view this as a projective invariant. And so these are really Plucker coordinates on the Grassmannian 2n, which is sort of where we're taking our matrices to be in. Okay. Then what happens if we consider all n choose 4 cross ratios that we can get from our n marked points? This actually gives us an embedding of M0n into an algebraic torus of dimension n choose 4. And there are some very nice relations that the image of this embedding satisfied, and this cut out set theoretically M0n. And these are sometimes called the cross ratio relations. And they're just really given by playing around with this type of products. And so basically we get 3 relations between all the different permutations of the indices I, j, k, l. And then we get some relations that relate cross ratio I, j, k, l to 2 other cross ratios where we have sort of this intermediate m. And one of the geometric reasons why this embedding is very nice is because if we take the closure, the Zariski closure of this embedding in P1 to the n choose 4, this retrieves what is called the DMK, so the Ligne-Mumford-Knudsen compactification of M0n, which is given usually in the description of genus 0 rational stable curves. So this is a very explicit way to realize this, this compactification, and therefore it's a very nice embedding. But now I want to tell you that in sort of the setting that we were considering, we actually want to work with a better parametrization, or I mean, that's to be seen, but we want to work with a different parametrization. So maybe let me go back for a second. So maybe one observation is that the dimension of M0n as a variety is n minus 3. This you can see, for example, by looking at the fact that we can always gauge fixed 3 points. And so we have n minus 3 sort of like coordinates left to play with. But here we are embedding into a much, much higher space. So this is clearly a much, much bigger dimensional space. And let's say I want to try to embed into something smaller. And one way to do that is to consider what I will call the dihedral parametrization of M0n. So for this, we are going to consider an n-gon labeled with vertices 1 to n. And for every chord in this n-gon, I am going to consider a dihedral coordinate. And this will just be a special cross ratio. So in this case, the cross ratio we're considering is I plus 1, j plus 1j. And using the cross ratio relations that I showed you before, we can obtain the primitive U relations. What are these primitive U relations? They are given by this. So for every dihedral coordinate, if we take the product of all of the dihedral coordinates corresponding to the chords that cross it, then this has to add up to 1. And this you can really check just by replacing the definition of the cross ratio, and then you will get the equality. And Francis Brown in 2009 showed that, well, he introduced this map, and he showed in particular that this gives a close embedding of M0n into an algebraic torus of this dimension, so n choose 2 minus n. And he also showed that the image is cut out set theoretically by the ideal given by this relations. Okay, so let me show you an example. So if we consider M05, then we need to look at this nice pentagon. And in this case, well, we have 5 chords, and each one of the chords has a very similar looking U relation. So for example, for chord 1, 3, we want to look at what are the chords that cross it. So in this case, we get 2, 4, and 2, 5. And therefore, the U relation that we get is U13 plus U24 times U25 equals 1. Okay, so far so good. But okay, let me tell you one more thing is I actually don't have only one dihedral parametrization, strictly speaking. In this point, I chose to label my n-gon in a very particular way. So I chose the ordering 1, 2, 3, 4, 5. But I could have labeled this n-gon completely differently. I could have chosen any cyclic permutation of 1 to 5, and then I would have gotten different cross ratios, different U variables with similar relations. And this would technically be giving me a different parametrization, but equivalent, but different parametrization of M0n. So for example, for n equals 5, we actually have 12 possible orderings. So in general, the number of cyclic permutations is always n minus 1 factorial over 2. And that gives us 12 for n equals 5. And we get this, all of these 12 possibilities. This will be important later on when I talk about sign patterns, so I wanted to just note it.
Hey, Veronica, could I ask a quick question?
Yeah, of course.
Why is it just the cyclic permutations? Just to double check.
Oh, yes. So this is basically because here if you rotate or reflect the n-gon, so basically up to any symmetry of the dihedral group, all the chords you get are the same and the crossings are the same. So you end up with exactly with the same cross ratios.
I see. So this gives the exact same embedding.
Exactly. It gives the exact same
Okay.
embedding.
Yep. Makes
Yes, it
sense.
does.
Thanks.
Mhm. Yeah. Um, okay, so this ideal of these primitive U relations actually also contains a larger set of relations that can also be described by some combinatorics of the n-gon. And maybe just for uh, to be exactly precise, um, in his original proof on 2009, Francis Brown actually includes this in the definition of the ideal, and then it was later shown by Thomas Lamb that they actually are implied, this extended U relations, and so it's enough to consider that the ideal is generated by the primitive U relations. Okay, so what are these extended U relations? So we're going to take any cyclically ordered partition into exactly 4 parts of the set of 1 to n. And then we are going to consider, we're going to group the dihedral coordinates in a very special way. So this is a lot easier to see with a drawing. So let's say that the way that I do this cyclic partition is from 1 to somewhere. And then we have, so this is my set A, this is my set B, this is my set C, and this is my set D. And then what the U relation that's going to be satisfied is that if I multiply all of the dihedral coordinates corresponding to the chords that go from A to C, so this is this term, and then I multiply, and then I add the multiplication of all of the dihedral coordinates corresponding to the chords that go from B to D, this actually has to be equal to 1. So this one can also sort of verify using these cross ratio relations. But it's a very nice set of relations. And somehow the idea is that you're grouping some vertices and looking at U relations in a smaller n-gon. Okay, so let me give you an example for n equals 6 of what the extended U relations look like. So in this case, we have 9 dihedral coordinates, again, corresponding to the 9 chords in a hexagon. And if I do the same procedure as before and I take any one of the chords and I look to what crosses it, I'm going to obtain these 9 primitive U relations. And besides this, we have 6 further extended U relations. So here I drew out for you one very concrete example. So what happens if I take my cyclic partition to be A is going to be 1, 2. Oh, oops. Sorry. So A is going to be the set 1, 2. B is going to be the set 3. C is going to be the set 4. And D is going to be 6, 5. And then in this case, the U relation that I get is exactly this one. So we get U14 times U12 plus U36 times U35 has to be equal to 1. Okay. And now with this definition, I can introduce the 2 types of sign patterns that we want to consider in M0n or in the real points of M0n. So if we consider a sign pattern, so this will be any assignment of a plus or a minus for each of the dihedral coordinates. I'm going to consider the orthant that it defines in R to the n choose 2 minus n. So what I mean by this is I am just looking at the part where these signs are satisfied for our coordinates. And we're going to say that the sign pattern is realizable if when I intersect this orthant with the real points of M0n, which by this I mean, for example, that we consider that all of the zi's are real, or of course infinity, which will in particular imply that all the cross ratios are also real. And so we intersect that M0 and R with our orthant. And if that is not empty, then our sign pattern is realizable. And we say that it is consistent if it does not contradict the extended U relations. So what do I mean by that? I mean, if I look at all of the possible relations coming from all the cyclically ordered partitions into 4, and I replace the uij's by a +1 or a -1, depending on the sign pattern, and I get that this can be achieved, that means that not both of these products are negative, are positive, no, sorry, are negative, that not both of them are negative, then this means that my sign pattern is consistent. Okay. And what is our main result? Well, our main result is that, and this I didn't write, so this is just by definition, it's going to be the intersection of the orthant with M0 and R. So this intersection is non-empty if and only if the sign pattern is consistent. Or equivalently, all consistent sign patterns are also realizable. And because of our proof strategy, we also show that in case that this intersection is non-empty, then it is actually connected. It will be one of the connected components of M0 and R. And it's going to be isomorphic as a semi-algebraic set to the positive points, which means asking all of the u's to be positive. And this answers a special case of a conjecture in a paper called Cluster Configuration Spaces by Arkani-Hamed, He, and Lam. So this will correspond to the type A case, in case any of you have ever seen this paper. And a little bit the tension that's happening here is very similar to it's very similar in vibes to realizable matroids versus non-realizable matroids. So you somehow have some combinatorial condition, which would be this consistency condition, and you want to check which one actually corresponds to a point that can be realized in a geometric space, which in this case would be the moduli space. Okay, so now I want to tell you a little bit about how the proof strategy goes, but maybe let me stop for 1 minute to see if there are any questions about the dihedral parametrization and
What exactly was the conjecture 11.1 for type A?
yes. So the conjecture is because, so in this paper, cluster configuration spaces, they define a lot of the things that I have said until now. So basically from here, they do it in more generality. So here, instead of starting with M0n, you start with a finite type cluster algebra. This would give you some set of indices to index your U's. And you also get some parametrization, you get some relations. There's also some moduli space, or what they call cluster configuration space, which is a quotient of the cluster variety. And then you can also define extended U relations. And then once you have extended U relations, then you can define again sort of this realizable versus consistent. And their conjecture is that for any cluster configuration space, consistent sign patterns are all realizable. And so in the type A case, so if you start with a type A cluster algebra, then when you do all of their construction, you retrieve M0n as their moduli space. Yes, so.
Thanks.
Yes. Yeah, so maybe since you asked, I'll make the comment that the technique that we use is very much hands-on. So it's like we're just really playing around with all of the structure that M0N has. But this has an advantage for one other sort of type in cluster algebras, which would be type C. So this is also obtained by folding some type A, and then we believe we didn't really work it out, but it's very closely related to type A. So we think that then this result can be used to also prove the conjecture in type C. The other types are more complicated, but yes. Okay, so let me tell you a little bit about what the strategy of the proof was. So for this, let me first tell you how you can relate sort of sign patterns to connected components of M0N. So a very nice known result is that the connected components of M0 and R are actually in bijection with dihedral orderings or cyclic permutations. Here I use them interchangeably. And how does this go? Well, I can represent a cyclic permutation by an element or by a coset given by the symmetric group modded out by the dihedral group. So this is really to consider all possible labelings of an n-gon up to rotation and reflection. And if I have this, so for every permutation here, the connected component that it will correspond to is where the points are ordered once I permute the labels by this permutation. And so in particular, the identity, which would correspond to the usual order 1, 2, 3, 4, 5, until n, corresponds to when you already chose the labeling of your points to be ordered. And this is what would be actually M0 and R plus or R positive. So this is sort of the way to go in between connected components and dihedral orderings or permutations. And now from there, it's relatively easy to go to realizable sign patterns. This I will explain just in a minute, but somehow the idea is that as I was mentioning here, if I label the n-gon in a different way, then I get a different dihedral parametrization. In particular, each labeling would correspond to a particular order of my points. And because all of our points are real, then they have to fit into one of these exactly. And then that particular dihedral parametrization, the one that corresponds to the order that I chose, or the order that my points have, will yield that my point is actually in the positive part. But okay, I'll explain a little bit more later, the details of exactly how you do this. But sort of the big picture is that we have a lot of different dihedral parametrizations, and we can go back and forward between each of these by using the cross ratio relations. And this will allow us to sort of map all of the connected components into a copy of M0 and R plus. And because this change of charts will be actually monomial maps, this will guarantee that the sign patterns are all determined. Okay, so this is sort of the first step. And then, well, we have some clear containment between realizable sign patterns and consistent sign patterns, just because, of course, all the extended U relations make part of the ideal that comes out M0N. And what we did with Hannah was to show that these two are equal by building a dihedral ordering from the consistent sign patterns. So if you give me a consistent sign pattern, I will give you a dihedral ordering in which that sign pattern actually corresponds to the positive part. Okay. Okay, so let me tell you what the main ingredient of our algorithm or all of it is, and these are these monomial maps. So as with basically anything that happens in the symmetric group, we're going to build it up from transpositions. And so let me consider a transposition in Sn that permutes two adjacent vertices in a labeled n-gon. So now here I'm assuming that I'm started with some labeling, an arbitrary labeling. And now I want to permute two vertices that are next to each other in that labeling. Then there is a monomial invertible change of coordinates between the two dihedral parametrizations. What do I mean? Okay, let me give you an example, which is the easiest way to understand this. So let me assume that I am starting with the standard or the identity dihedral ordering, where I take 1, 2, 3, all the way up to n. And now I want to swap 1 and 2. And I want to go from the dihedral parametrization that corresponds to this n-gon to the one that corresponds to this n-gon. Well, for this, what am I going to do? Well, I can actually use the cross-ratio relations. So let me denote with uij the dihedral param or the dihedral coefficient, the dihedral coordinates for the usual m0n, so for this n-gon. And let me denote with Vij the ones that correspond to this n-gon. So for the order 2, 1, 3, all the way up to n. And here, just using cross-ratio relations, we actually see what the map is. So the first observation is that if both I and j don't touch 1, 2, or n, then I plus 1, j plus 1, j, they are all exactly the same as before. Somehow where I did this transposition is not affecting this chord. And so the dihedral coordinates are the same. If I take something that touches n, then using the cross-ratio relations, I would get that this actually corresponds to multiplying 2 of the old dihedral coordinates. Very similarly, if I choose something that goes with 1. Now, if I choose something that goes with 2, I have inverted one of the older dihedral coordinates. And if I take the very special chord 1n, I get a much more complicated expression. But what is the nice thing about these monomial maps? Well, let's assume that I started with a sign pattern where the only negative chord was this. So n2. Too little. So let's assume this was our only negative chord. All of our other coordinates were positive. Well, if I do this map, all of this stays positive, all of this stays positive, all of this stays positive, all of this stays positive. And because this one here was negative, I have now turned this into a positive coordinate. And this is sort of the idea or the observation that led us to sort of pursue this strategy. And it's because now we want to start applying all of these transpositions in a way in which we are somehow correcting or making positive all of the negative chords that we have. And so also to give you more of a pictorial interpretation of what's happening. So as I was mentioning before, if I make, let's say more in general, a transposition AB, the only chords that are affected are the chords that touch these 3 vertices. And they have one particular formula. So the orange formula corresponds to this. So it comes multiplied by the one before. The blue ones are also going to be multiplied, in this case, by the one after. Then all of the purple ones will be inverted. And then we have this special red chord that will have this complicated expression, but that we still have some control of the signs with. And it's actually this minus sign here what allows us to actually eventually get to an all positive sign pattern. Okay, and now I claim that only because we have these monomial maps, this is enough to actually show this bijection here. And so what is the idea? So the idea is that if I have any cyclic permutation, I can write it as a product of adjacent transpositions. And once I have that product of adjacent transpositions, this will give me a map, a monomial map, from any connected component of M0 and R to the all positive part in a different dihedral parametrization. Because this map is monomial, so in particular is a nice map of semi-algebraic sets, and then everything will behave nicely. And after that, all you have to show is that you have as many realizable sign patterns as connected components to actually get a combinatorial bijection, because you have already shown that there you have a way to go from the dihedral orderings to the sign patterns. And as I mentioned before, so we know we have n-1 factorial over 2 dihedral orderings or cyclic permutations. And a way to count how many realizable sign patterns there are is by using a different way to view M0n that I didn't present here, but is to view it as a complement of a hyperplane arrangement. And then it just amounts to counting regions. And that count is also done in another paper of Thomas Lamb. But yes, sort of the idea here is that just by doing some smart counting, you can get this. Now, getting this will be slightly more complicated, as I will try to explain, even if I won't go into the details, because the proof is really a bit of a sign chasing among monomial maps. Okay, so what is the idea? The idea is, as I was saying before, given a consistent sign pattern, we want to produce a dihedral ordering. And so I want to produce a dihedral ordering that satisfies the following condition. If I take the corresponding monomial map, so this is what I was saying, so I have a dihedral ordering, I write it as adjacent transpositions, and then I take the composition of all of the maps, as I was describing before. I want that when I map the intersection of M0 and R with the orthon corresponding to my sign pattern, I get exactly the positive part. So this we can also denote as M0 and alpha R positive. So I want to get exactly the positive part in a different, so this alpha here denotes that I'm using a different dihedral parametrization. And honestly, the idea of the algorithm, I would say, it's rather naive in the sense that I think it's what one would just start doing when we're doing an example. So we start with the sign pattern. We take the shortest negative chord. Well, of course, if it's not already the all plus sign pattern, we take the shortest negative chord. And we want to apply the transposition that swaps the elements in this chord. So maybe let me draw a little thing here. So let's say that I start, so I always start with this order. And let's say that I have a chord ij here. And this is the shortest negative chord. Okay, I didn't mention, but so what do I mean by shortest? It means that, okay, so I can measure the length of a chord by looking at one of the two sides, depending on which one is shorter, and counting how many vertices there are. So on the side that we have less vertices, that's what I call the shortest, the length. And so for the shortest negative chord, what I'm going to do is that I'm actually going to swap I plus 1 and j. So I'm going to swap them, and then we're going to land in some parametrization that looks like this. I, then I'm going to have here j, I plus 2. We're going to have j minus 1, I, j plus 1. And so we have swapped. So this is I. Sorry, I plus 1. We have swapped I plus 1 and j. So this is what this line is telling you. There is a bit more of notation that was needed, but so the idea is that we always take the shortest negative core, and then we swap I plus 1 with j. And somehow the intuition behind that is we are trying to make the sign of discord. So what now here would be discord. I'm trying to make discord have positive sign. So this is somehow the idea. And then we basically just iterate this algorithm. And our proof is, or basically what we prove, like to be more formal, is that this algorithm actually terminates if you start with a consistent sign pattern. So you're always going to end up in the all plus sign pattern. And the concrete way that we do that is that we show that this invariant, so this invariant for the sign pattern, so the pair of the number of negative chords and the length of the shortest negative chord, always decreases after a finite number of iterations. So this is a little bit delicate because, of course, when we started doing this, we were really hoping that in every case, after only one iteration, we would decrease either the number of negative chords or the length, but this is not necessarily true. So there are some very badly behaved sign patterns in which doing this type of swaps will actually increase the number of negative chords. But if we keep iterating, we will eventually annulate or like reduce enough of the negative chords. And this is where the more technical part of the or sort of our project comes in, is this analyzing all of these cases and arguing why you always decrease. So now I want to show you how this works in an example, because I think it's the easiest way to do it. So if we consider a tangon, and here the red chords are the negative chords, what will be our sign pattern. This is consistent. And now I want to start applying the algorithm. So the algorithm starts. Oh, and I realized I actually drew this. I marked the wrong thing. So it starts, and so the shortest negative chord is this one right here. So you see that this only has one vertex on this side, and so technically we will call this length 2 chord because it has 1 and 2. Okay, and so we apply the algorithm and we obtain this sign pattern here, in which we have swapped 7 and 8. Now the next shortest negative chord here is this one. And again, we apply the algorithm, we swapped 9 and 10. And now we obtain that this is the shortest. And so here we swap 4 and 6. We obtain this. Now this is the shortest. Again, okay, we swap again and we obtain this. Here we swap, we obtain this. And I didn't put the last step, but here we will swap 5 and 4. And we will obtain the all positive sign pattern. So one thing we can already see here is, for example, you see that even in this simple case where I have only one negative chord, I need several iterations to actually clear out this chord. And here what we are decreasing is the length of the shortest negative chord, and then we eventually just sort of eliminate it. Okay, so this is it for what I wanted to say about these dihedral sign patterns. And sort of, yeah, so if you're interested, the paper is in the archive and you can look it up. Are there any questions before then I talk about some ongoing work?
So just so I'm understanding how this algorithm works, at each step you're either removing one of the negative sign patterns or like decreasing the length. And so,
Yes,
okay,
exactly.
I see.
Yes, so for example, in all of these ones, you are decreasing the number of negative chords in your sign pattern. And here you're just decreasing the length of the shortest negative chord. Yes. Okay, then let me talk to you about blowing down things instead of blowing them up. So somehow maybe let me say a little bit more about the motivation of this current work. So this is now joint work that it's on progress with me and Hadley Frost. And what is the idea? So the idea sort of comes on my end from the fact that all the work that we did with Hannah, even if it did prove Oh, I think I disconnected. My Wi-Fi disconnected for a second. Okay, so I'm not sure at what point I disconnected. But
I think your audio cut out, but you're back now.
okay, great. Yes. So, right. So what I want to say is that sort of the motivation for this project is, or one of the motivations is to find a much more elegant proof of what we did with Hannah. And it's like somehow not just like sign chase and sort of like brute force the sort of the result, but to really have like an elegant way of doing it. And we believe that a possible way of doing this is by actually considering some varieties that are a lot more simpler than M0N. And what I mean by a lot more simpler, concretely, is that they're given by doing iterative toric blowdowns of M0N. And even if this sounds like very fancy words, or at least to me it sounds like very fancy words, it's very easy in the sense that we're just doing some monomial projections from M0N. So here I wanted to show you the example of M06. And what is the idea? So for every n, we actually get a poset of algebraic varieties, which are connected via monomial maps. And so for M06, we're going to get 4 other varieties, and they're going to be connected in this way. And so what are the sort of the equations of these varieties? They will all be given by U relations, very similar to the ones from M0N. And they all correspond to these monomial projections. So to go from M06 to P6, which is called the Pelitope or the Pell space, for most of your variables, you're going to have now 8 variables indexed by 1, 3, 1, 4, 1, 5, 2, 4, 2, 5, 2, 6, 3, 5, and 4, 6. So almost all the chords in your hexagon except one chord. So for almost all of them, so except for V35 and V46, except for these two, they're going to be exactly the same as the U variables for M06. So really the map will just be a projection. And now for these two special 3, 6, 4, 6 variables, they will come each of them multiplied by the missing chord by U36. And then to go from P6 to U1 and U2, we're going to do something very, very similar. So again, so we're going to reduce in only one variable. And this one variable that we reduce will be multiplied into two other variables. So here the W's, all the W's except W25 and W46 will be equal to the V's. Similarly here, the W tildes except W14 and W35, they will all be the same as the V's. And then these ones will be given by these products. Okay. And then we're going to have this C6 at the end, which is really just going to be a hypercube. So this one is going to be defined by three equations. So this one was going to be the vanishing of three equations. So I'm going to have 6 variables, and they're going to satisfy these three equations. And then there is a way that you can get them from monomial maps from U1 and U2. And this is what I wrote down here. I think it might be too small to see. This is somehow just giving what the monomial maps are, but it's the exact same concept as here. So we are reducing from 7 to 6 variables, and we're only changing 2 of the variables where we're multiplying in the missing variable. And so in this setup, for every variety, we're going to get U relations, which are all given by the projections of the U relations of M06. We're going to get consistent sign patterns again in these extended U relations. And the very nice thing is that at the bottom, there is always a hypercube. And the nice thing about the equations of the hypercube is that it's very easy to see what are the consistent sign patterns. Because the only options that you have are that they are both the UI and the UI prime are positive, or one of them is positive and the other one is negative. And the question is, can we recover all consistent sign patterns of, okay, so of M0n in general, so for M06 it's true. So can we recover all the sign patterns of M0n via the monomial maps? So can we always find a way to go up from the hypercube to M0n and somehow trace back this n-1 factorial over 2 sign patterns that we would want to find at the end? Yes, and I think that's everything that I wanted to say. So of course, if you have any questions, I'm happy to answer. And if not, then thank you again for having me.
Thank you so much, Veronica, for a wonderful talk. Are there any questions? Okay, I might have a couple of questions. So in this example here, so if we fix a 0, 1, and infinity, and we view M06 as the complement of the hyperplane arrangement in three-dimensional space, could you comment quickly on what's happening geometrically under these maps? So does this correspond to like collapsing some regions? For example, the map from M06 into the Pell space, and then also from the Pell space into these other.
Yeah, so maybe let me give you a modified answer because
Okay.
I actually haven't thought about what happens at the level of the hyperplane arrangements.
Mm.
But you can definitely think of the positive part of all of these regions to be equivalent to some polytope, right? To be like a diffeomorphism to a polytope. For M06, you get the three-dimensional associahedron. When you're doing to the associahedron to go to the polytope, is that you are collapsing one facet. You're collapsing one of the square facets. And then you do the same to go from the polytope to, so in this case, U1 and U2 are isomorphic. And they're exactly the same. And then you collapse another one of the facets, another one of the square facets.
Where? Okay. Okay.
And then when you collapse the third one, you get the hypercube.
Yes.
And so you're always doing this. And for higher dimensional things, I don't like to think about collapsing facets because I can't see that. So the easiest way to think about it, at least for me, is if you take the normal fan of the polytope, you're doing coarsenings of the normal fan.
Okay.
And this is why these are toric blowdowns.
Yep.
You're just coarsening the fan.
Cool. And then another question. So does this mean that the number, so for fixed n, that the number of consistent sign patterns is just the number of regions, both bounded and unbounded for M01? Okay.
Yes,
Okay,
exactly.
great. Yep.
I may have missed this. Is it possible to like describe what the hyperplane arrangement is for which M0n is the complement?
Yes, of course I can. I didn't say it actually, so
Oh,
I
okay.
I totally skipped it. But it's actually quite relatively easy. So for this, you really have to do a gauge fix, or I mean, the easiest way to do it is to do a gauge fix. So we fix this to be 0, let's be more consistent. You fix this to be 1, and then you fix that n to be infinity. And then your hyperplane arrangement will be given in C to the n minus 3, where I'm going to index the coordinates by Z3 all the way to Zn minus 1. And then your hyperplane are going to be where they're equal, or where they're equal to 0, or where they're equal to 1. And then you take the complement of that, that will give you M0n.
I see. Okay, thank you.
Yes, and so for the, now I'm gonna probably get it wrong. For the, you get this for M05.
Any final questions for Veronica? Okay, if not, I'll go ahead and stop the recording.